American highways crack in 7 years. A third of US bridges are structurally deficient. The concrete sidewalk in front of your house was poured in 1998 and is already crumbling. Now look at the Roman pier in the harbour of Caesarea Maritima, off the coast of modern Israel, poured by King Herod's engineers in 22 BC, submerged in salt water for 2,047 years. The concrete is not falling apart. It is growing aluminum tobermorite crystals inside itself that make it harder every year. The Pantheon dome in Rome has held itself up since 126 AD, 43 metres across, with no steel, no rebar, and no major repairs in 1900 years. The recipe behind both buildings was documented by Vitruvius in 30 BC and rediscovered by MIT, UC Berkeley, and Princeton in the last 20 years. Volcanic ash, quicklime mixed hot, crushed pottery, aggregate that gets lighter as you go up, lime crystals that reseal cracks the moment water touches them. Almost none of it has ever appeared in a bag of modern American cement. These are the 7 Roman concrete secrets that modern construction companies have spent 100 years burying. Number 1. Pozzolana, the volcanic ash from Pozzuoli. Walk down to the Bay of Naples, 16 kilometres west of the city. The town there is called Pozzuoli. By the year 79 AD, when Mount Vesuvius buried Pompeii, this town had been shipping its volcanic ash to every harbour in the empire for 2 centuries. Vitruvius wrote about it in 30 BC in De Architectura, Book 2, Chapter 6. He said this ash, mixed with lime and seawater, set into a stone harder than the cliffs on which Rome was built. He was not exaggerating. The Romans were exporting roughly 250,000 tons of pozzolana per year by the 2nd century. Volcanic ash is glass, blasted into the atmosphere by an eruption full of reactive silica and alumina. Mix that glass powder with lime and water, and the silica and alumina bond into calcium aluminum silicate hydrate, a different mineral than what Portland cement forms, stronger, slower setting, self-healing. In 1824, an English bricklayer named Joseph Aspdin patented Portland cement. Portland was cheap, fast, and could be made anywhere with a limestone quarry and a coal fire. Within 50 years, it had replaced pozzolanic concrete worldwide. The Roman recipe still worked. It just was not patentable, and the volcanic ash source was 800 kilometres from the English steel mills. The Pozzuoli ash sat in its warehouses for the next century. You do not need to fly to Pozzuoli to mix this yourself. Metakaolin, the calcined kaolin clay sold to potters, is the cheapest and most reliable substitute. Pumice powder from a masonry or aquarium supplier works just as well. $30 to $50 for 40 pounds. 1 part by volume in your mix. That single ingredient does what Portland cement cannot. Bay of Naples ash worked. The next ingredient was hiding in every kiln for 2,000 years, until MIT figured out the Romans had been mixing it wrong on purpose. Number 2. Hot mixing with quicklime, the recipe error that ran for 2 centuries. In January 2023, an MIT engineer named Admir Masick published a paper in Science Advances. He had been studying samples from the walls of Privernum, an archaeological site about 100 kilometres southeast of Rome. The walls were poured around 30 BC, still standing. Under the electron microscope, the samples kept showing small white chunks, 1 to 3 millimetres wide, embedded in the concrete matrix. Modern chemists had been calling these lime clasts for 50 years and assumed they were defects. Sloppy mixing by Roman workers. A flaw in the recipe. Masick ran X-ray diffraction. He tested fresh concrete mixed 3 different ways. The lime clasts were not flaws. They were the entire point. For 200 years, every Western textbook has taught the same recipe. Start with slaked lime, calcium hydroxide, the white powder you buy at the masonry supply. Mix it with water, add your ash, add your aggregate, build. The Romans did not do that. They started with quicklime, calcium oxide, the hot caustic powder you get straight out of a lime kiln before water touches it. They mixed the dry quicklime directly into the pozzolana and the aggregate, then added water last, all at once. The reaction is violent. Quicklime hitting water reaches 150 degrees Celsius in seconds. The mix steamed for hours. The lime clasts that survived the violent reaction stayed in the wall as reservoirs of unreacted calcium carbonate, sitting there for centuries, waiting. Modern manuals taught the slaked version because slaked lime is safer to handle, easier to ship, and easier to standardize in a factory. The textbooks lost the technique that mattered most. Masick put it back on the table in 2023. Almost no commercial cement plant has changed since. If you want to try this yourself, the safe path is Type S hydrated lime, $10 per 50 pounds, mixed with water before the other ingredients. The Roman path is Type Q quicklime, dry mixed with your pozzolan and aggregate, water added last and fast. The Roman path bakes the self-healing clasts into the wall. It is also caustic enough to burn skin on contact. Leather gloves, safety glasses, and a respirator are non-negotiable. The reservoirs in those walls were doing something specific. The third secret was hiding above your head all along, in the dome of the most visited Roman building in the world. Number 3. The aggregate gradient in the Pantheon dome. In 126 AD, Hadrian completed the Pantheon in Rome. The dome above the rotunda is 43.3 meters across. The largest unreinforced concrete dome ever built, holding itself up for 1900 years without any steel, rebar, or major repair. The Romans solved the weight problem by changing the recipe as they built upward. The lowest 12 meters use heavy basalt and travertine, the same dense stone that paved the Appian Way. The middle uses brick and ceramic rubble. The upper section uses lightweight tuff, a porous volcanic rock that floats in water. The crown, closest to the oculus, uses pure pumice, 800 kilograms per cubic meter, against 3,400 for basalt. The dome gets lighter as it gets higher. The weight at the base loads onto 8 relieving arches in the drum. The weight at the top, where collapse would normally happen, drops by 60% through aggregate choice alone. The 9-meter oculus is held open by shear compression geometry. The Pantheon does not crack because nothing inside it can rust. Modern reinforced concrete pours from one truck with one recipe. Same mix at the base as at the crown. The variable that lets you build a Pantheon was traded away for assembly line efficiency. Cheaper to specify steel rebar and let it rust on schedule. On a home scale, you do not need to gradient your mix unless you are building a dome or a vault. For a flat footing, a garden wall, or a fire pit, one mix with basalt aggregate is fine. 2 grades, 3 to 6 mm fine and 10 to 20 mm coarse. 4 parts by volume against 1 part lime and 1 part pozzolan. The crushed greystone landscapers use for French drains is exactly the right thing. 3 secrets so far. The 4th broke into mainstream news in 2023, and 3 commercial laboratories have been trying and failing to replicate it since. Number 4. Self-healing concrete, the lime-clast mechanism. This is the discovery that broke the story in 2023. Masick's team cast a Roman-style sample using the hot mixing technique, cracked it under load, and dripped water through the crack. 2 weeks later, the crack was sealed. The matching samples mixed with the modern slaked lime recipe stayed cracked. The mechanism is almost embarrassingly simple. Picture a hairline crack opening in a Roman wall. The lime clasts embedded in the mix are reservoirs of unreacted calcium carbonate. When water reaches a clast, it dissolves it. The dissolved calcium flows into the crack as a saturated solution, and when it loses the water by evaporation, it recrystallizes as fresh calcium carbonate, the same mineral. The crack fills itself in real time, and the wall keeps standing. Masick published in Science Advances in January 2023. Marie Jackson at the University of Utah confirmed the same mechanism in her own marine samples. Every concrete wall they examined, from northern Britain to North Africa, contained these lime clasts. Modern concrete contains none. Now look at what this means for industry. The American ready-mix concrete market is worth roughly $76 billion a year, and the bulk of it is replacement work. Bridges that fail in 50 years, sidewalks that crack in 20, parking garages that spall in 30. If concrete healed itself the way a Roman wall does, the replacement market would collapse. Two MIT spin-offs have been working on commercial self-healing concrete since 2018, using biological additives, encapsulated polymers, and bacterial spores. The cost per cubic metre is roughly 4 times the cost of standard Portland. The Roman version costs almost nothing extra. The only difference is the mixing temperature and the order of operations. Dozens of patents have been filed since the 1990s, and most of them sit in the vaults of large cement manufacturers, unused. If you are wondering how that is even legal, so is everyone else. If you use the hot mix from number 2, you have already built the self-healing into the wall. The lime clasts are sitting in the matrix, waiting. You do not need a biological additive or an MIT spin-off product. Every hairline crack that opens in your slab over the next 1,000 years will close itself the next time water touches it. Number 5 is older than the Pantheon. The Romans called it cocciopesto, and they lined every aqueduct in the empire with it. If you are finding value in this investigation, subscribe. Medieval Way digs up the things modern industry would rather you forget. 3 more secrets to go: the aqueduct lining, the pier that gets harder underwater, and the steel reinforcement trap. Number 5. Cocciopesto, the crushed pottery aqueduct lining. We have 3 Roman techniques above ground and 1 in the laboratory. The next one is what made every Roman city possible: the water supply itself. In 144 BC, the consul Quintus Marcius Rex completed the Aqua Marcia, the longest of the 11 aqueducts that fed Rome. 91 kilometers from the springs of the Anio Valley to the urban distribution tanks. Roughly 187,000 cubic meters of water moving through standing pipe, channel, and arch every day. And it had to do it without leaking. The Romans lined every meter of the aqueduct with a mortar called cocciopesto. 3 parts crushed terracotta pottery, 2 parts lime, 1 part sand. The pottery was ground to a fine pink dust from broken amphorae, roof tiles, and kitchenware. When you fire clay above 800 degrees Celsius, the silica and alumina in it are partially activated, the same way they are in volcanic ash. Fired pottery dust is Pozzolana you can make in any kitchen kiln. Cocciopesto is waterproof, slightly flexible, and self-healing through the same calcium carbonate mechanism. The Aqua Marcia ran for almost 500 years without major repair. The Pont du Gard in southern France used cocciopesto on its upper conduit and was still partly functional in the 17th century. A modern concrete water main has a design service life of 50 years. The cement industry today uses 0 ground pottery in its standard mix. This is one of the simplest medieval recipes you can mix in an afternoon. Save broken pots, broken roof tiles, terracotta planter rejects. Smash them into a fine pink dust with a hammer and a heavy canvas bag. 3 parts pottery dust, 2 parts hydrated lime, 1 part sand. Mix to a stiff paste. This is the right mortar for the joints in a garden wall, the floor of a fish pond, the inside of a rain cistern. Anything that has to hold water for decades. Coxia pesto lined the aqueducts. The next secret built the harbours, and it is the only concrete on Earth that gets stronger the longer it stays underwater. Number 6. Seawater concrete, the marine mix that strengthens underwater. 22 BC. Caesarea Maritima, on the coast of what is now northern Israel. King Herod the Great is building a deep-water harbour on a stretch of coastline with no natural bay. His engineers pour concrete blocks the size of small houses, lower them into 30 metres of Mediterranean water, and cement them to the seabed. The pillars they build still hold up the foundations of a harbour that no Mediterranean state has built since, anywhere, which looking back was either incredibly brave or incredibly stupid. Marie Jackson, a geologist at the University of Utah, spent a decade sampling those Caesarea piers. Her papers in American Mineralogist, between 2013 and 2017, traced what happens inside Roman marine concrete after it cures. Two things in sequence. First, the seawater dissolves trace elements out of the volcanic ash, aluminum, silicon, magnesium. Those elements precipitate inside the concrete matrix as aluminum tobermorite, a rare crystalline mineral geologists otherwise only find in hydrothermal vents. The tobermorite crystals interlock with each other and with the existing calcium silicate hydrate gel. They strengthen the concrete. Second, over centuries, the seawater continues to react with the lime in the matrix. Phillipsite, a zeolite mineral, grows into every microfracture in the concrete. Phillipsite pulls salt out of the seawater and locks it into the structure. The concrete becomes a carbonate zeolite composite that gets harder and denser every century it stays wet. Modern Portland concrete does the opposite. Chlorides from the saltwater penetrate the matrix, find any embedded steel, and rust it. The Tappan Zee Bridge in New York, opened in 1955, had to be replaced in 2017 because its steel-reinforced piers were dissolving in the Hudson estuary. The replacement is rated for 100 years. Caesarea has done 2,000 and counting. The biggest mistake every homeowner makes is letting a fresh pour dry. Roman concrete needs to stay wet. Cover it with damp burlap and spray it once a day for 28 days, twice a day if it is hot. Modern Portland hits 80% of its final strength in 7 days. Roman concrete hits that strength at 6 months and keeps gaining for another decade. After 28 days, strip the form. The slab should ring like a stone when tapped with a hammer. It should not chalk under your fingernail. If it crumbles, your lime was too old or your Pozzolana was unreactive. Break it up, mix the pieces into your next batch and start again. Lime is cheap. Your foundation is not. Number 7. No rebar, and why steel reinforcement was the worst thing that ever happened to concrete. Everything modern construction had built into concrete was about to work against it. If the industry had stopped at gravity-loaded design, this would be a very different story. Instead, in 1854, an English plasterer named William Wilkinson patented the idea of embedding wrought iron bars inside a concrete floor slab. The concept was extended to steel in the 1860s by Joseph Monnier, a French gardener. By 1900, reinforced concrete had taken over civil construction worldwide. Steel rebar has one fatal property: it rusts. The rust occupies up to 7 times the volume of the original steel. That is not a typo, by the way. When water and oxygen reach the bar through hairline cracks, the bar swells, the concrete cracks open further, and the structure fails. The American Society of Civil Engineers, in its 2025 infrastructure report card, estimated that the United States faces more than $3 trillion in unfunded infrastructure repairs by 2033. That is the kind of number that makes accountants cry. The single largest contributor is corroding rebar. The Romans did not put steel in their concrete. They did not need to. Roman concrete was designed for compression loads only. Every major Roman structure was geometrically arranged so that gravity pulled everything into compression. The Pantheon dome works because every stone pushes down on every stone below it. Arches do not need rebar. Compression-only structures do not need anything that can rust. Sometime between 1880 and 1900, the concrete and steel industries made a structural decision. Concrete would be designed as a tensile material, with steel doing the tensile work. This unlocked flat slabs, cantilevers, and skyscraper floor plates. It also locked the industry into a 50-year replacement cycle. The rule for anything you build yourself is simple. Compression-only structures get no steel, garden walls, fire pits, foundation footings, fence post bases, chimney pads, root cellar arches. Build them in compression with Roman-style concrete and they will outlast you and your grandchildren. The moment you need a flat slab to span a gap, you are out of Roman territory. That is a steel job, and the rain will eventually eat it. Or redesign around it with an arch instead of a beam, and never replace anything. Each of these 7 techniques solves a problem that modern construction created. Concrete that loses strength in seawater, mixes that crack and stay cracked. Aqueducts that leak in 50 years. Slabs that fall apart because the steel inside them rusts on schedule. The Romans did not solve those problems with magic. They solved them with volcanic ash, quicklime, crushed pottery, basalt rock, and the discipline to keep their paws wet for a month. Every one of those ingredients is sitting in a supply store within 40 miles of your house. The chemistry was published by Vitruvius in 30 BC, confirmed by MIT in 2023, and verified at UC Berkeley and Utah in the decade between. We traded the Roman recipe for assembly line speed and a 50-year replacement cycle. We traded gravity-loaded geometry for steel-loaded beams that the rain will eventually destroy. We traded buildings that stand for 2,000 years for buildings that need to be rebuilt before the people who paid for them retire. The recipe was never ours to lose because it has never been lost. If this investigation was useful, subscribe to Medieval Way. We are digging up everything modern industry would rather you not know how to do for yourself. Stone, lime, ash, wood, fire. Drop a comment and tell us which of these 7 techniques you are going to mix first. Lime is cheap. Your foundation is not. Let's keep digging up what they buried.